we can put some security issues in place, like a CM and IDS. We can do cyber threat information sharing. Eventually, the device will go over an update process because we have a new software update, we have to apply mitigation, and at the end of the life, it goes over the decommissioning process in which we remove data or we repurpose the device. So as you can see here, we have many actors involved in this life cycle that are providing or generating a lot of information. So we have the manufacturer that is generating, for example, the list of components, the BOMs. It may generate the expected behavior in terms of a manufacturer usage description, some recommended configuration. The certification authority can generate an assessment report, a certificate. During the deployment, we deal with the secure configuration. During the operational phase, we deal with all the CD information, with vulnerabilities, with evidences that are valuable for certification. For the upgrading, we deal with the different version of the software, with maybe updates over the list of components or vulnerabilities, and so on. So we have a lot of information, many actors involved, and the idea is to put in the center of all this ecosystem a matching readable document, which we have called a security passport. So the idea is to centralize all the information in a single matching readable document, so all the different actors of the life cycle can share the security information related with a specific device. This is valuable not only to enable collaboration between them, but also to support for example, certificate composition, because if we have access to the security information of the small pieces of the system, we can use this information to certify a bigger system. Also, if we are collecting evidences during the operational phase, we can use this evidence to support agile recertification in case we detect some security change. And also we can support agile mitigation. If someone detects a vulnerability, the manufacturer can release a mitigation, and the mitigation can go over the passport to the operational phase, to the operator, to enforce this mitigation in the operational context. So how we envision this passport? Well, for this, we are using OSCAL models. OSCAL is a set of models developed by the NIST, by the National Institute of Cybersecurity of the United States. And the idea is to use it as the meta model in which we can link all the external information that is generated by the different actors. So for example, the list of hardware components, the HBOM, the list of software components, the SBOM, the behavioral information in terms of network, which is the manufacturer usage description, threats and mitigation in terms of threat mood, vulnerability tracking, for example, using Vexel on VDR, certificates, evidences, requirements, updates, all the information in a single place. The idea is not to embed all the information directly in the OSCAL models, but to use some links to the external information. Why? Because First, because each of these external information, the majority of them already have a standardized format. For example, SBOM has Cyclone DX or Sweet Tags or SPDX, so we don't want to reinvent the wheel. And also because if something changes, and security is quite variable, if we detect a vulnerability, we don't want to regenerate the whole passport. We just focus on the external source. So this is the structure, the internal structure of the passport. As you can see, it's like a monster because we have a lot of information that could be included inside. And in the colors, you have the OSCAL models. So we have the blue one, which is the catalog. It is used to represent a database of requirements, of security requirements. Then we have the other blue, the blue on the right, which is a profile. The profile is used to select which subset of these requirements we want to evaluate over the target of evaluation. The green ones are to define or to describe the information about the components and the system. So here we have mapped all the information about the bill of materials, HBOM, SBOM, CBOM, AI bomb, whatever, and also the mood file. In yellow, you have the assessment plan. So it's how we plan to assess the requirements over this target of evaluation. The orange one is the most important because it's the assessment result. And here we put all the information that we have collected after the assessment. So for example, which requirements we have assessed, which is the target of evaluation, of course, linking with the other models, which tools we have used for the assessment, attestation evidences that we have collected, vulnerabilities that we have identified, and mitigations. And on the top of the passport, we have the latest red model, which is the POAM, the Plan of Action and Milestone, in which we have important information like the device unique ID and additional information that we have put here to comply with the European Cyber Resilience Act. I don't know if you are familiar with this regulation, at least if you are from Korea or Japan, but this is a regulation that is created in Europe and is mandatory for the manufacturers to use some kind of vulnerability management, to be transparent with the information. So we have included additional information, for example, contact information for the manufacturer or technical information, the unique identification of the device, the European Declaration of Conformity, and the external information that is already present, like the software bill of material, is mandatory due to this regulation. Measures for secure commissioning using this MUD file, security issues using VEX and BDR, and support for mitigation using the threat MUD file. This passport has been used for now in 2 different European projects. The first one is DOS. DOS is focused on the supply chain management, and the idea is that we have some testing that we are applying over the device before it goes to the runtime, and we have also components that are focused on providing this onboarding over the operational platform. Well, here, the most important component related to the passport is the DSP platform in red. And this platform is in charge of managing all the information of the passport and providing access to all the components of the DOS architecture and also to the different actors, to the manufacturer, the operator, and integrator. Of course, we have put here some authentication and authorization because some of the information contained in the passport is sensitive. In DOS, the passport is not something static, it's something that has its own life cycle. Because, for example, the manufacturer is generating a generic passport. The manufacturer doesn't know where the device will operate, doesn't know information about the operational context. So the information that can put here is information that is valid for any kind of device of a particular model. So, for example, for a Raspberry Pi. So the manufacturer can include some metadata, contact, certificates that has this device, bill of materials, MUD, information about vulnerabilities. And then for each specific Raspberry Pi, following with the example, we have an instance of this passport, including the unique ID for this specific device and the cryptographic keys using the CBAM. Then when the device is sold, we go to the operational domain. And here, the operator or the integrator takes the role of extending the information that is included in the passport, because we already have information that is contextualized in a specific domain. So we can, I don't know, add new libraries. So we have changed the SBORN. We can detect new vulnerabilities that are specific for this domain. So we are adding new VEX or BDR files, and so on. So we extend the information of the passport depending to the context. All the passports are linked. So if the manufacturer adds a new vulnerability to the generic passport, this information will also be received in the instant passport. So all the actors are connected. And the other project in which we have used the passport is Cobalt. Cobalt is more focused on security certification. And here we use a digital twin to make some kind of copy of the real system. And we are extracting evidence from the security digital twin and certifying the security of the real system based on this evidence. So focusing on the passport, we have here the CCM manager in the center of the architecture that has a similar role in DOS to manage all the information, all these OSCAL models. and to provide the access to the information that is contained inside. Also, in this project, we consider Hyperledger to store all the information and providing integrity and auditability. So here in Cobalt, the most important information that we are using from the passport is the blue models. If you remember the part of the security requirements, which tools are used, how we are assessing the security requirements. We are saying that, for example, OSCAL is not capable of, for example, replicating metrics, so we are trying to extend a bit more the passport to fulfill the requirements for certification purposes, but more or less this is the idea. So, and just to finish, as a recap, well, we have defined this passport based on the OSCAL NIST models that are collecting all the information from the different phases of the life cycle, generated in principle by the different actors or tools that are placed in there. So we have information, list of components, expected behavior, certificates, etc. And the idea is that this collection of information is not only supporting the collaboration among these actors and these phases of the life cycle, but we are also guaranteeing some valuable properties that indeed are properties that are mandatory in this European cyber resilient regulation. For example, the transparency of the vulnerabilities and tracking of vulnerabilities, if this vulnerability is active, is being studied, if it's solved. Information about the recommended configuration to ensure a secure by default configuration. This is also mentioned in the CRA. We are also supporting the sharing of knowledge in a collaborative way, which is in line with another regulation, other European regulation, which is the NIS directive. We have information about the certificates to support the composition. And we have also information about mitigation and vulnerabilities, supporting this vulnerability management, quite important in the Cyber Resilient Act. So in a whole, I mean, we have this matching readable file in the center of all the ecosystem, in the center of all the stakeholders, that is facilitating the secure management during the whole life cycle. Because, I mean, the power of managing the cybersecurity is precisely in the actors that are involved in the life cycle. As future work, I think our main plan is to focus on how to automatize the usage of the passport, not only to generate the information, because you have seen that it's a lot of information, but maybe also to use LLMs, for example, to detect new vulnerabilities that were not included here. So we are going through this way. Okay, so that's everything for now. Thank you so much to everybody. Yeah. Okay. I don't know if you have any questions. Please don't hesitate to ask me.
Thank you. Okay, first of all, thank you very much for your presentation. I think it was very interesting. You mentioned that this OSCAL model, that it is that you are using. My question was, why do you think it is gaining this attraction among all the alternatives that may exist?
Yeah, I mean, OSCAL was initially defined by the NIST, which is from United States, but it gained attraction thanks to a project called Medina. And they created the initiative, which is the EuroSCAL, the OSCAL friends from Europe. that they are using OSCAL. And since that, it's gaining attraction because, for example, in Cobalt, we are contacting with ENISA, which is the European Agency for Cybersecurity, because as you may know, we have some certification schemes in Europe, and one of them is the scheme for cloud, certification, and we are trying to, or they are trying to map the requirements of the cloud scheme to OSCAL profiles and models. And we have also been contacted by EXO, which is the European Cybersecurity Organization, to create a task force regarding OSCAL. So, I mean, there is some initiatives over in Europe moving information about OSCAL. So, and also there are some industries behind that, because IBM, for example, or Amazon are also interested in OSCAL. So, I mean, for now, it seems a promising set of models. Let's see in the future, but for now, it seems promising.
Great, thank you.
Just one short question. What about privacy?
About privacy.
There is a lot of information there, but...
Yes, that's the point. We have centralized all the information of security in a single place. So, of course, we need some mechanisms for authentication and authorization. So, in those, for example, that we have put this mechanism in place, we have a FIAM that, mainly the manufacturer decides which blocks of information should be shared with whom. So, for example, I don't know, public vulnerability information. Vulnerability information is private and is only for the certification authority. And the information about certificates is valid for everyone. So the manufacturer decides the visibility of each block of information.
Okay. Yes.
Okay. So... Sorry. Okay. So the following talk will be presented by Jorge Gallego, and it's called Replicating Network Topologies Through the Use of LLMs. Authors are Ramón Sánchez Iborra, Jorge Gallego Madrid, and Antonio Escarmeta, Javier Prieto, and Mahmoud Abbasi.
Okay, so thank you very much for the introduction, Sarah. As you mentioned, I'm going to present our work, the replicating network topology through the use of LLMs. Here, I don't know if... here's the outline of the presentation. So, as an introduction, we are during this last year, under an unprecedented change with the next generation of mobile communication, first with 5G, then we are starting to work on 6G. And with them, we have unprecedented challenges in terms of network management, network orchestration, monitoring, etc., in the different segments of the network. So this brings a problem that is the enlargement of the threat surface, because with this new generation of services, applications, architectures, interfaces, and etc., we have an enormous threat surface for novel and unknown cyber attacks. Under all these changes, we have two new, let's say, technologies or concepts that are bringing a lot of attention lately, that are the network digital twins, that can be very useful to evaluate these threatening scenarios without disrupting the normal operation or the regular operation of the system, and also the LLMs, the famous LLMs that are present almost in our everyday life now, which have huge capabilities for a lot of things. For example, for the automatic creation of network models from heterogeneous data, and can support the generation and the operation of network digital twins. The contribution of this work is basically that we consider this an initial work into a completely new research line, and we focus on the first step of the network digital twin, that is the creation process of the network digital twin, and the configuration of this virtualized network topology that replicates the real physical network deployed in the infrastructure. So what we are doing is we will evaluate well-known LLMs to generate these network digital twin topologies. As an output format, we chose to use Container Lab framework topologies because it is gaining some attention among academia with Docker environments that are easy to use, and it was a nice point of testing to evaluate and to do a performance evaluation of the production of these topologies. Some related work to contextualize this is that during the last year there has been some different methodologies to generate these operational network digital twins. For example, data processing for the real network, so you can infer some information, use of generative AI. Here we have the LLMs we mentioned, for example, and also advanced algorithms, not, let's say, AI based, but similar. And past works on this matter have done different approaches. For example, processing pipelines from packet capture traces or generic algorithms and neural networks to do the generation of the topologies. Also, automatic generation algorithms that do this work, or a typical one that is graph sample and aggregation of devices. And finally, of course, generative AI with federated learning or generative twins to infer this complex network. However, we have several challenges. For example, the accurate modeling of complex network and the performance of these LLMs when extracting information from the real network or from the different models. And this is what we are going to address in this work. A little bit more of context regarding the convergence and these synergies between the network digital twins and the LLMs, which can suppose a milestone for technological innovation, because with this convergence at network level, we believe that we can achieve significant improvement in the management of the network. Also, it will help with the virtualization, obviously, because it will be easy to create these network digital twins. And finally, a general improvement in management, orchestration, monitoring, maintenance, lifecycle management of the network as a whole, using these LLMs, this network digital twin supported by the LLMs. With them, we can have real-time dynamic monitoring and simulations of the real scenarios, and advanced processing and knowledge generation. So regarding network digital twin platform that we considered, there is a wide range of tools with different characteristics. Obviously, we have the the basic ones that are the simulators that basically simulate the behavior of the network. They simulate the protocols, but are not real. Okay. Then we have the emulators that are similar to the latter ones, but they implement and support the use of real operating systems, so we can have a little bit more of realism in the scenarios. Then we move on to the cloud environments that are very well known. For example, Amazon AWS. That can permit the use of network digital twins. So, for example, Microsoft Azure, that already implements some digital twins software and frameworks to replicate the status of their devices in some sense. And finally, we have on-premise virtualization solutions, that these are more custom, let's say, made solutions based, for example, in Container Lab, or even simply in Kubernetes or Docker, because you can also have a replica of the network there. In this context, the role of the LLMs is basically here in the configuration of digitalized topologies. That is basically the first step in the pipeline of generating network digital twins. The strength of the LLMs is that they can receive a variety of unstructured inputs, and with this information that is not organized, not as I said, a structure, they can construct a foundation of data for the system modeling. With all this, inferring some knowledge. We know they are not perfect, but they are a really powerful tool that we can benefit from. These LLMs will take inputs of different types. Here we consider different ones, and then in the experiments we implement 3 of these ones. For example, they can have this topology mode where you explain them the topology. They have, for example, a configuration file, not configuration file, a descriptive language describing the network. Also, they can infer from the network equipment configuration files directly how is the network, how it is configured. We also have passive modes, for example, network fingerprinting, in which different agents distributed along the network can detect what is happening on the devices and how they are interacting among each other, so they can infer the topology. And finally, a picture of the topology. This is the simplest one, a simple picture of the topology that is obviously made by hand or by some kind of these auto-generating softwares. And finally, a natural language description that can be, for example, simply, okay, the network is in this way, it has these routers, they are connected in this way with this host, this operating system, and so on. It's simply a natural language description in everyday words. With this, we move on to the experiments. We consider, as I said, this is the first work we are doing in this research line. So we consider 4 well-known and general LLMs, with no specific purpose, no fine-tuning, nothing, let's say, special. We use Microsoft Copilot using GPT-4 with the academic license, and then in their free license versions, Anthropic Cloud 4, Google Gemini 2.5 Pro, and Perplexity AI. I think 4 of them are well-known and extended. The target output, as I mentioned, was Container Lab. So the idea was that the LLM processes this input and then generates the topology that we are aiming for. Container Lab is basically a tool for the development, operation, and management of virtual networks. It uses simple configuration files, and it can run on any platform supporting Docker. So the idea is that our LLM generates a structured configuration file that you can see on the right, the template, describing the network. So we can directly deploy it using Container Lab. Okay, and that would be one step forward in the automation process of this network digital twin generation. As inputs, we have 3 different network topologies with distinct complexities, and we chose these types of inputs: natural language description, a raster image, and a network model in JSON, a custom JSON made, nothing not standard, it's just a description, a structured description of the network. Here you can see the input prompts that were fed to the LLM. In the first one, we have this natural language description, in which, as you can see, create a topology using the following network, and we describe the network. It has one router running Nokia 00 OS. It is connected with this and that. Okay. The second one, we attach the image, the raster image, in which we say to the LLM, okay, you have here the image of the topology. Please generate the configuration file in Container Lab. And finally, with a JSON, a structured JSON, in which we say, okay, here you have a general configuration of the network. Please generate the same, but for Container Lab. Here is the 3 raster images, a simple complexity one, medium, and high, although these can be scaled until the infinitum. So, well, these ones are just for the experiments. Here you have an example of the JSON. As you see, it's just a structured format, nothing special. And then, you already saw the natural language prompt that it's already shown there. In the experiments, we aimed at analyze the capabilities to port these network topologies into an structured container lab network model. Okay, so these results were evaluated through human inspection, and in the first one we can see the performance of these LLMs for the simplest complexity topology. As you can see, we have Cloud and Copilot that performs very well, although Gemini and Perplexity failed. Gemini failed in the implementation of the operating system. It confused one system from another, and Perplexity missed the description of the links between the routers using a technology that was not described there. Then with the medium complexity topology, in this case Gemini and Perplexity did it very good. But Cloud and Copilot failed with the picture and the JSON. In this case, the missing parts were, again, they confused some operating systems. For example, one it is that used Nokia, but it used Ubuntu or something similar, and they also missed the links. They did whatever they want with the links and put another technology. And finally, with the highest complex topology, we have even more fails that is expected. Cloud failed, Gemini did it good, and Perplexity and Copilot also failed, again with the operating system, missing some links, not missing, but confusing some technology from these links. For example, I don't know, Ethernet, instead of Ethernet, they put serial and so on. And also they missed, Copilot missed some routers from the topology when translating it. So as a conclusion, we evaluated this intelligence and efficiency of modeling and deployment the virtualized network. We evaluated the performance of these 4 well-known LLMs with promising results, but as I mentioned, Gemini overall was very good, but the generated configuration are not fully trustable, and we had errors of various types. For example, we saw that raster images and natural language introduce more errors. However, the JSON structure format seemed like the more, obviously, you may think, generated the more accurate output. And then, well, we have a new landscape of innovation and functionality for the 6G that is coming with these network digital twins and LLMs. Obviously, there are a lot of further lines in this process, but our next focus lines will be not using generalist LLMs, but try to find someone more specific for these tasks. And finally, as I mentioned, use some specialized fine-tuning that fits better this purpose. And well, that's everything from my part. Thank you very much for listening. And if you have any question, I will be happy to hear them.
Okay, thank you so much, Jorge. I don't know if anyone from the audience have any questions. Okay.
Thank you. So thank you for your talk. It was very interesting. I have a question regarding, are you using anything to validate the output of the LLM?
In this work, no. We did the evaluation by hand. I mean, human. It is human done. Mm-hmm. It was validated both syntactically and semantically from both perspectives. And until this point, we did not have this automatic, let's say, validation or just another way of validating it. But right now we are working on the use of for example, the own LLM to validate the output. I mean, for example, telling the LLM, okay, I said to you this was the prompt, but you failed here. Oh, well, and this is the output. So please check that the output corresponds to the input I provide to you, both syntactically and semantically.
Okay, thank you.
Thanks.
Any other question? Okay, I have a curiosity. because now we have the boom of the LLMs, and we use LLMs for everything. So after your experience, do you think it's worth the work? I mean, if you still need to check all the information that is produced and they have variable errors, do you think it's still worth?
Thank you for the question. I think it's a very important and relevant question right now. I have to say that I believe that at the beginning, for starting, we are in the conception stages of the LLMs, so to say. We know the LLMs a few years, at least as a generally public, and I think they still have a lot of improvement ahead. In this case, I think they are a really powerful tool, and they fail, obviously. But the idea, I think, is to progress towards a more accurate results. And obviously, well, in our, for example, in our research line, we are thinking of using the own LLMs to correct itself, because we have observed that in some cases you can correct it just by saying, "Did you notice that you failed? Please," or well, using the please is optional, but please try to see what was your error. And for example, well, it's not here, but we have seen some promising results in our initial experiments, just using the own LLM to correct itself. But yes, I think they are not fully trustable, but I think that the power that it's within that paradigm technology, whatever you want to say, it surpasses the disadvantage that we have right now, and I think that for the future they will be very useful.
Okay, thank you.
Thank you very much.
Okay, any other question? If not, let's thank the author. Thank you so much, Jorge.
Thank you again.
Okay, so next presentation is online, so we'll watch the video. So the title of the talk is Prioritized Multi-Criteria Optimization for Efficient Cloud-Native Application Resource Allocation, and it's presented by I don't know the name. Polythois Song, please.
Yeah.
Okay, so let's see.
Hello everyone, my name is Polythois Soulis. I'm a postdoc researcher at the National Technical University of Athens in Greece, and I'm here to present you our work entitled Prioritized Multi-Criteria Optimization for a
Hello, sir. Can you mute the mic first, maybe? Because it's something like a noise. Thank you.
efficient cloud-native application resource allocation. In this presentation, I will discuss an approach to solving the resource allocation problem in the edge cloud continuum, moving away from the traditional optimization methods towards a prioritized intent-based mechanism that better reflects the diverse needs of applications. This is the outline of my today's presentation. Initially, I will do an introduction on the motivation behind our work, specifically looking at the complexity of the edge cloud continuum and the limitations of current allocation methods. Next, I will define the system model, covering both infrastructure and our novel modeling of application intents. Then I will detail our proposed solution, which includes an exact mixed integer linear programming formulation and a fast, greedy heuristic. Finally, we will examine the performance evaluation results before concluding with our future directions. Let's begin with the challenge at hand. We are witnessing a shift toward the edge cloud continuum. There is no longer a flat, homogeneous environment, it's a hierarchical infrastructure. At the periphery, we have the near edge, which is the layer populated by diverse resources with limited capacities like Raspberry Pis, NVIDIA JSON, or Cloudlets. They offer minimal latency for real-time processing, but they are expensive to operate per unit and have limited capacity. And at the core, we have the cloud. Here the resources are abundant and operational costs are lower due to economies of scale. However, accessing the cloud incurs significant networking cost and a high latency penalty. Simultaneously, the applications themselves are evolving. We are now dealing with cloud-native architectures and applications that are decomposed into smaller, loosely coupled microservices. Crucially, these microservices are not uniform. They have diverse and often conflicting requirements, ranging from real-time data processing to strict energy efficiency and fault tolerance. And this creates a massive orchestration gap. As we move toward intent-based networking, where users define high-level performance goals, the traditional weighted sum objective function fails. It is incredibly hard to tune. Trying to find a numerical weight that accurately represents a strict priority, like I need low delay above all else, is a cumbersome and often leads to inaccuracies. Before we explain our solution, we must clarify what we mean by application intent. In traditional networking, operators had to manually configure low-level parameters like specifying exact bandwidth allocation or CPU cores. However, in modern intent-based networking, we shift the focus from the how to configure to what to achieve. An intent is a high-level abstraction. It allows users to describe their desired outcome, such as high throughput or low latency, without needing to know the details of the underlying infrastructure. But here is the catch. Intents are rarely simple. Users have multiple conflicting goals, and they want high performance and low cost. To solve this, we introduce the concept of intent combined with a tolerance factor. Let me explain how we handle these conflicting objectives using a culinary analogy. Cooking a stick. Imagine you are ordering a steak and you have a hierarchy of needs. The first priority is doneness. You want it medium rare. That means that it needs to be cooked at 54 degrees of Celsius. And the second priority is efficiency. You want it to be cooked quickly. In a traditional weighted sum approach, you mathematically average these goals. The algorithm might interpret this as cook it at a high temperature for a short time, resulting in a steak that is lukewarm but served very fast. And that is a failure. Our approach respects the hierarchy. We prioritize the temperature first, however, we introduce a key feature called tolerance. You might say, I target 54 degrees of Celsius, but I will tolerate a deviation up to 58 degrees of Celsius if it allows for a perfect sear. We apply the exact same logic to the cloud. An application defines a priority list. Latency first, then energy, for example. In this case, the tolerance tells the system, I want the best possible speed, but I'm willing to sacrifice a small percentage of performance, for example 10%, if it allows us to optimize the next goal, which is energy, and to optimize it significantly. This turns a strict constraint into a flexible optimization range. Now, let's formalize this into our system model. We model the infrastructure as a hierarchical graph. The nodes are partitioned into near edge, far edge, and cloud. Crucially, every node is defined not only by the CPU, RAM, and bandwidth capacity, but also by its operational cost and its latency profile, which is related to the distance from the user. On the workload side, each application is a graph of microservices with data flow dependencies. Our decision problem is straightforward. For every microservice, we must select a node that satisfies its constraints while respecting its specific priority list. So, to summarize the problem, we are dealing with complex applications spanning the continuum with conflicting criteria. Traditional methods oversimplify this by aggregating objectives into a single objective function, often prioritizing global infrastructure goals over specific application needs. Our contributions are twofold. First, we propose a lexicographic framework with a sequential optimization mechanism, and we solve for priorities strictly in order. For example, first delay, next cost, and next energy. And also we have a tolerance flexibility. We introduce this factor to permit bounded deviations in higher priorities to unlock gains in lower ones. And to achieve this, we propose two mechanisms. First, we model the problem as a mixed integer linear programming formulation, multiple mixed integer linear programming formulations that are solved sequentially, and we solve repeatedly iteratively for its intent. Hence, for iteration t, we minimize the cost of the current priority metric. The constraints ensure that every service is placed exactly once. The node capacities in CPU, RAM, bandwidth are fully respected, but the most important constraint is the last one. This equation dictates that the value of any previous objective cannot degrade more than the allowed tolerance, while we optimize the current objective. This mathematically enforces the stick analogy we discussed earlier. While the mixed integer linear programming formulation provides the optimal solution, it is computationally heavy for large systems. For real-time orchestration, we need speed, and therefore we developed a greedy heuristic. This algorithm approximates the lexicographic behavior through a process of filtering and pruning. Here is how it works. First, we process applications one by one. For a microservice of the application we examine, we find all nodes that meet capacity constraints. We rank those nodes based on the first priority metric, for example, latency, and we calculate the best possible value, apply the tolerance factor, and discard any node that falls outside this range. We then re-rank the remaining nodes based on the second priority and repeat. This captures the spirit of the prioritization, but allows for near instant execution. To evaluate this, we set up a simulation environment representing a 3-layer edge cloud continuum. We simulated 35 near edge nodes, 15 far edge nodes, and 5 cloud nodes. We deployed 50 cloud native application workloads, and we defined 3 distinct intent types to mimic real-world scenarios. Type 1 workload corresponds to ultra-reliable low-latency communication and prioritizes delay over energy over cost. On the other hand, IoT workload, which is type 2, prioritize energy over cost over delay. And the third type of workload, which corresponds to broadband traffic, prioritizes cost over delay over energy. Now, let's look at the performance result. First, execution time. The optimal solver took an average of 112 seconds to solve the sequence. On the other hand, the heuristic took only 0.13 seconds, which is a massive improvement in speed. Second, the optimality gap. For type 2 and type 3 workloads that optimize first energy and cost, respectively, the heuristic is extremely accurate with a gap of less than 6%. On the other hand, for type 1 workload, which optimize first the delay, the gap is slightly higher at about 17%. This is expected because delay-sensitive resources at the near edge are scarce, creating high contention with a greedy approach struggling to resolve them perfectly. However, for real-time orchestration, the heuristic provides a viable trade-off. Now, this slide demonstrates the impact of the priority orders on the actual resource placement. The bottom graph shows the allocation percentages. As we see, type 3 workload, which has the cost as priority, pushes the workloads to the cloud and far edge resources. This matches exactly the intent, as cloud resources are cheaper. On the other hand, the type 1 workload, which has the delay as priority, the system utilizes the near edge resources significantly more to meet the latency targets. Also, when we prioritize delay, that is the type 1 workload, the cost and energy bars, as you can see, spike up to 3 times compared to the other types of workload. This confirms that low latency is an expensive luxury, while cost and energy objectives are largely compatible, at least for our experiments. To conclude, we have presented a prioritized multi-criteria framework that allows operators to model intents as lexicographic orders. We proposed both an exact mixed integer linear programming formulation and a fast heuristic mechanism. Our key takeaways are that priority orders yield predictable trade-offs, and our heuristic offers near optimal performance at a fraction of the computational cost. For future work, we plan to incorporate time-varying traffic for dynamic reoptimization and integrate the logic of intents and tolerance into an orchestration mechanism that leverages machine learning in order to perform the ordering of intents for the different applications. Thank you for your attention. I'm happy to take any questions.
Okay, thank you so much. I don't know if you are online.
Yes, I'm online.
Okay, perfect. So, anybody from the audience have any questions? Okay, I have to say that at the beginning of the presentation we have some sound issues, so we
Yes,
we,
no worries.
we couldn't follow the beginning of the presentation. Okay, so from my side, I just wanted to know. You told at the end of the presentation that as future work you were planning to do some dynamic adaptations. So
Yes.
this means that you are considering, for example, machine learning to adapt if if it's more priority at the cost, or later it changes to the energy or whatever, or do you mean it's more on the line of changing between the algorithms between ILP and greedy?
No, for sure, machine learning is an option, the best option basically, because it has a fast execution time. What we try to do here is we argue that when you want to optimize multiple criteria and the input is an intent, selecting exact values for its intent, for its objective, is a difficult task which cannot be calculated accurately. So if we use a machine learning model, as you said, that performs this ordering of objectives from the most important to the least important, this can adapt, this can have a better, let's say, mechanism that translates intents to resource allocation. So the mechanism here is the connection between the machine learning model you said in order to perform this intent-based resource allocation.
Mm-hmm. Okay, that sounds interesting. Okay, thank you so much. Any other question? Okay, so thank you so much. Let's turn the auto. Okay, so the next presentation is announcing privacy multi-domain network internegotiation and will be presented by Pedro Martinez Julia. So it's your turn.
This one. Okay. Hello, everyone, and those online also. Thank you for presenting me. I will talk short today. Last year, I presented one strategy to resolve what we can say network intents in a multi-domain approach, like we used a multi-agent system to do so. At the beginning, our network intents had the shape of natural text, let's say English, but we preprocessed them and we began working with one structure that is not plain text, has some preprocessing, and then we use this multi-agent system to finish all the processing and obtaining the formal representation of the service we want. So from that point, I will show now one evolution of that to enhance the privacy on this multi-agent system to minimize the information shared among those agents. Sorry, so not moving. Okay. So as I mentioned before, we aim to maximize the privacy, so minimize the amount of knowledge, we talk about that, or information we share among the agents that are involved in the resolution of this network intent. As I mentioned before also, the multi-domain network resolution comprises many things at the same time. This is using a multi-agent system, that's it, to resolve one network intent that is talking about one network service involving only one domain, or one network service that involves different domains. In this scenario is what we focus particularly, because we demonstrated also that each agent is the best one to resolve the part of the network intent that each domain will manage. So that's the best trade-off we found. So what we advanced from that point is to study the information shared and minimize it. We have evaluated our proposal to demonstrate that we achieve our claims. So first, we introduced the network intent resolution. This is what will be done, no, in an abstract way. Yes, first, we begin sending one agent what we call the goals, that is the output of the preprocessing of the network intent in natural text. So those goals are normally we begin with one text or one set of sentences, and we aim to get one, in our case, one network service description for OSM. That's the goal that the multi-agent system must achieve. So the first agent receives that goal. Then it gets the premises of this goal. No, is what we know about the goal, what we know about the network intent, and what we know about the network service at this point. Then we also obtain the let's say, the knowledge base of this agent, and then we make inference, we infer new knowledge items using all that information. Here is the point that, that will be a bit sensitive, because some, let's say, bad agent can try to extract information using this function, this inference function. Later I will mention how to resolve this, not resolve, but minimize this point, this problem. So after that, what we do is that to check if the goal has been achieved, and if so, the process finished. If not, we find another agent and we send all the information that we had before and the new inferenced knowledge to the next agent, and the next agent will do the same and until the goal is achieved or there is no remaining agents to ask. At the end, we have a fully resolved network intent, so we have a JSON structure, there is a network service definition, or there are some points that are not resolved. So in order to improve the privacy of this algorithm, of this approach, what we did is to first what we did is to modify the way the next agent is selected. So we first ask all agents to get what we call the resolution potential from the original network intent. It's not Here, what we send to the next agent in each case is the new information, let's say the new knowledge, after processing the old one, the previous one. So in each step, we are advancing towards the solution. In this modification, and here we use the find next agent is any, for example, round robin or whatever algorithm we can use. And in the modified function to find the next agent, we consider the original network intent. We ask all agents what resolution potential, how many concepts they will be able to resolve from this network intent, and we consider all that to sort the agents and finally return the agent that will resolve the most number of concepts. With this, what we aim is to limit the amount of information that is shared after that agent. And as we use this function in each agent, at the end, we expect to minimize the amount of information shared among all the agents in this multi-agent system. Okay, so we evaluated that by measuring the amount of concepts that were exchanged, sent actually from one agent to the next one. And we, in one scenario that resolved many network intents and different configurations of this multi-agent system. With the previous algorithm, the previous way, what we had is what see here is from C1, configuration 1 to configuration 6, and we have different amounts of information shared, because depending on the position of the agents in the network, we can end up sharing more or less information. With our proposal, we make sure that the minimum amount of information, as we can see here, is C6, is achieved using the algorithm, the find next agent I presented before. So we evaluated this, and this algorithm, as I presented, will ask all the agents for the potential amount of concepts that they will resolve. So this can introduce some overhead, but we also validated that the total time used for resolution is what we call feasible, because it is in line with some of the configurations of the worst. Yes, but they are existing configurations in our previous version of the algorithm. So without incurring in a large amount of time in this case, we could minimize the amount of information shared among the all agents in the resolution system. And that's, as I said, it was being short, and that this is the end of my presentation.
Okay, thank you so much. Any questions from the audience? Okay, I have one curiosity. So you are trying to minimize the information that you are sharing. I'm curious, do you try to analyze if with the information that you are sharing, I mean, they are capable of infer the information that you are hiding?
Sorry, yes. I didn't analyze that, but what we used is actually for evaluating the hidden amount of information, we used the information theory. So we evaluated the, let's say, the entropy that was changing in the process. So even though we do not know the particular information that was being shared, we know that there is more information because the entropy changes. So that's the idea. We didn't, if we wanted, we could use some kind of malicious way of using this achieve goal function, of inputting some network intent that is done particularly maliciously to get some particular information from agent. We can do that, but actually we only verified that theoretically using the information theory and the entropy. So there is information there, but we do not know particularly what information is being shared. Of course, there's not full security here because we must share something. We must share at least that if we have some knowledge, one agent has some knowledge that is required to resolve some part of the intent. After doing that, that agent will show some things that the agent knows that's required. But what we try to do is to minimize that, only that. But of course, there will be, and we didn't check that, which one is.
Okay. Thank you so much. If there are no more questions, okay, let's thank the author again. Okay, next presentation will be presented by Jaime Fuster. And it's Fuster, right? Fuster or Fuster? Fuster. Fuster, okay. Jaime Fuster. And the title is Defending Minds, Not Just Machines, an Agentic Approach to Cognitive Security.
Okay, thank you. So, okay. I hope the slides are updated. Okay, let's see. Okay, so yeah, I'm Jaime Fuster from NEC Labs. So first of all, we've noticed that, well, first, traditional security focuses on protecting IT systems. And we've noticed that we don't, in the future, we don't want to just protect IT systems. We want to empower people to make better decisions. That is, we want to go from defending systems to augmenting the human condition of the people who are protecting. So why human cognition? Well, modern cyber threats are increasingly exploiting human cognition as an attack surface. Like attackers are targeting the way people perceive and decide rather than just focusing on technical flaws. This shift is evident in recent statistics that show that recent breaches, 60 to 74% of security breaches involve a human element. And traditional defenses such as firewalls, antivirus, endpoint systems don't address this cognitive dimension, leading to a mismatch between cognition-focused attackers and technology-focused defenders. So the question that we wanted to ask ourselves was, could we build some kind of firewall for human cognition? So as an example, I want to start by describing the attempt of compromising xcutils, which is a known library that is very important critical dependency that is linked to many packages in to package management and many important projects such as OpenSSH in Unix-like systems and Linux. That was performed last year in 2024. So what happened is first a Microsoft developer discovered that he was, while using the latest version of xcutils, he realized that he was getting very slow SSH connections and high CPU usage. And then after checking the code and the project, he realized that there was a backdoor in the xcutils project. He contacted the community, and it was confirmed that yes, there was a complex backdoor that was included in versions 5.6.0 and 5.6.1 of xcutils between February and March of 2024. So what happened here? When they started to analyze the project, they realized that it was maintained by one single person that started in 2018. This is a project that is being used, as I said, like in most Unix and Linux systems. So it was maintained by one single person that was working as a volunteer, like during their free time. And they were working by themselves until 2021, when a user named Jiatan started submitting minor patches, helping with like unglamorous tasks, and doing like all the cumbersome jobs. And they started helping in 2021 until 2023, when suddenly new profiles started appearing and pressing for in the mailing list for new updates, suggesting more delegation, which led to the maintainer to give more privileged roles to Jiatan and let them take care of builds and tarballs and start. So what happened is Jiatan introduced the backdoor in xcutils, which was discovered in version 5.6.0 and 0.1. So if we analyze the attack kill chain, we see that there was first a selection of a target. Okay, the slides are not updated, but it's fine. The attacker realized that this was a vulnerable project. It was maintained by one single person on their free time, as I said. So very vulnerable. So they started to build trust between 2021 and 2023, doing like the unglamorous tasks, doing boring jobs, building credibility and gaining trust. This led to them then using this trust that they were getting to apply more pressure to the maintainer by creating fake accounts and using the mailing list forums to push a narrative for faster releases and more delegation, which led to the maintainer to give them more authority and allow them to make builds and tarballs, which allowed the attacker to create the backdoor and implement it into one of the releases. So as you can see, this is a way in which a thing in cybersecurity that is going on, and we are not making it up. Here are some findings from recent papers in top security conferences, which show that, for instance, things like tunnel vision, when you are very focused, when you get very focused on one specific thing because of stress, or people tend also to do complexity aversion, which is like we are basically want to avoid all the complex tasks. We tend to procrastinate as much as possible, especially when we are under stress. And also fatigue is also a big limitation that is affecting security, meaning you get a lot of warnings, a lot of requests for updates that make you pay less attention to security risks. Other cognitive limitations, well, yeah, here are some other examples. You can use what they call the authority and halo effect to, for instance, create deep fakes by pretending you're the CEO of a company, overload and habituation fatigue by sending millions of several multi-factor authentication requests, or like flooding a CM or a SOC system, and then spear phishing. So if we analyze the cognitive vulnerability surface, we can see that the targets of cognition warfare can be divided into three levels: micro, meso, and macro. The micro level would correspond to a single specific target, like in our example from before, it was the single maintainer of the open source project. There, some possible attack techniques could be like overloading with work, giving tunnel vision to the maintainer, etc. On the meso level, we have a targeted group of people, such as the employees of a company. Attack techniques like trust exploitation, habituation are very common in this area. And then on the macro, we can talk about, on macro level, we can talk about society, like manipulating public opinion, making disinformation, etc. So we want to solve this, and as I said, what we want is to, let me go back to here 1 second, to build some kind of firewall that can protect the human cognition, right? So how can we do it? In our opinion, the solution, there's a good opportunity right now of using generative AI agents for this, and I'll explain why in a minute. No. Okay, so right now, with in recent years, with the rise of LLMs, we've gone from being able to use LLMs passively through to what we call agentic systems with agents that are autonomous. There are recent breakthroughs that have moved beyond simple text generation to complex multi-step problem solving. We have things like deep research, which are agents that can autonomously browse, synthesize, and verify vast amounts of data. We can also have agents that are specialized in different execution flows, like codecs for coding or computer use for interacting with interfaces. But the thing that we are seeing is that all of these solutions are very centered on experts. They're built for power users, meaning like you cannot extract relevant insights from these tools if you do not know what to ask them for. They're always you cannot always only interact with them on demand, right? They're not running continuously in the background. They're not focused on the general public that maybe is not aware of like security, what to look for in like security contexts. So yeah, as I said, most Gen AI solutions nowadays are limited by the way they operate. They require humans to initiate the process, and they only work if people are already aware of the risks. So Gen AI today is great for experts in the micro level that I mentioned before, but it's limited at the meso and macro level. Our solution is to build we've proposed a framework that can be used that divides agents in different roles and tasks for this specific for protecting human cognition. So if we talk about like existing things like on-demand and assistive agents, like what we have with a ChatGPT, with a Copilot, etc. We could talk about advisors, right? You could have agents that can be used to gain specific insights, can use different tools to gather information and give important insights to a user. But then we want also to have something that is running continuously in the background and doing always on autonomous checks, small checks of policy, maybe like if an email is maybe phishing, etc. We call these sentinels that are continuous and autonomous, running in the background. Then we also define keepers, which are also run continuously, but on demand and are assistive. They are meant to be checking continuously the state of the system, notifying and proposing different fixes, but not taking any action, proposing to run executors which can perform more complex actions and can be similar autonomously with guardrails, and can be similar to similarly to current solutions like Codex or deep research. And then over all of this, we would need also a set of agents that can control the policy, privacy, provenance, and auditability of the whole system, and carrying and keeping in track of the memory of our systems. So if we go back to our previous example, we could have avoided the case of we could have used executors to automatically check for supply and supply chain changes by the Microsoft developer. Also automating tedious tasks so that the original maintainer didn't have to depend on an unknown person to run them. Keepers could be in charge of automatic identification of backdoors in the project, and also automatically checking the status of critical projects and detection of easy targets. And then sentinels could be used to automatically identify possible fake profiles. So in conclusion, we believe that cognitive security is a field that is more and more important in cybersecurity nowadays, especially with the advent of generative AI. So we want to protect human judgment and decision-making from manipulation and overload by completing technical controls and not replacing them. So for this, we believe that Gen AI agents are a good opportunity to solve this issue, and we proposed a framework, a solution that is a role-based agent blueprint based on sentinels, advisors, executors, keepers, and stewards that align speed with safety and offer a practical path for future research and development. Thank you very much. If there are any questions.
Okay, thank you so much, Jaime. Do we have any question from the audience?
Sorry, I have just more curious question. So you said generative AI used for this. Okay, yes. It's called generative for something. What are we generating here? Because I understand the part of that we are processing something, that we are processing text or whatever, but what are we generating in this particular, for example, in the example, what are we generating?
So I don't know if you are familiar with programming agents with LLMs.
A bit, but not too much.
Okay, so you now, like, I think people are doing more and more is using these large language models, so that's GPT-5, etc., to create programs that can make decisions and run by themselves. So the loop is being the model itself is like the reasoning of the autonomous program. Then you can, well, it would depend, right? Like I think Jorge or in the previous presentation, they were using LLMs to generate network topologies, right? So mainly in the agent-wise, it's like the brain of the program that is creating the reasoning, and then you can use this to, the model itself can call different tools that it can give different outputs, and then from those outputs make different decisions that would lead to the final response. So that's where the generative part is.
Okay.
Okay, any other question? Okay, from my side, I just wanted to know, you presented several kinds of attacks at the beginning at meso, macro, and micro level. Your solution will be able to deal with all the different attacks, or with a subset of them? I mean, it's the perfect
I mean, this is
solution.
a position paper, so it's just an idea that we have to keep researching on.
Okay.
And there's no system implemented, or I mean, we have agents that do different stuff, like aiding in our company. We have systems that we have a system that we've developed that aids our security team to gather cyber threat intelligence and different information from all around, from the deep web, from many different sources, and create different relevant reports and insights like continuously. So what we want is to think more broadly and like think of how could we, like, in the future help people to solve this, like to protect themselves from this cognitive type of attacks, from social engineering, etc.
Okay, thank you. I think it's interesting because we don't usually tend to think to the psychology behind the attack. So. Okay, if there are no more questions, okay, thank you so much, Jaime. Let's start.
Thank you.
Okay, so the last presentation will be also online. The title is Lightweight Secure Federated Learning for Energy-Constrained IoT, a case study in smart irrigation, and will be presented by Thora Dakia.
Hello everyone, my name is Zohra Dakhiya and I'm a PhD student. Today we will present our work on lightweight and secure federated learning framework designed for energy-constrained IoT devices evaluated through a real smart irrigation case study. The presentation is structured around 5 key points. First, I will introduce the overall motivation and challenge we address. Then, I will describe the real-world dataset and the federated learning system architecture. After that, I will explain our proposed framework which integrates lightweight security mechanism with energy-aware client selection. After that, I will present the experimental results we get and a comparison with alternative approach. At the end, I will summarize the key contribution and outline future directions. At the start, federated learning allows devices to train locally and share only model update, which is essential in domains like agriculture, healthcare, smart cities, where raw data cannot be centralized. However, bringing federated learning into IoT network, it's not straightforward. IoT devices are often battery powered, heterogeneous, and resource constrained, which limits how much local competition they can perform. At the same time, model updates transmitted across network are exposed to threats such as tampering. These two constraints, energy and security, are often treated separately. In this work, we integrate them into a single framework tailored for IoT deployment. Previous studies have made significant progress in improving efficiency using smart client selection or reducing communication. On the other hand, security mechanisms such as secure aggregation and differential privacy provide strong guarantee but at a high computational or bandwidth cost. For example, secure aggregation may require extra communication routes or cryptographic operations that small IoT devices cannot support. So the key research gap is designing a security mechanism that is strong enough but still lightweight enough for real IoT devices. This is exactly what we address in this work. Our dataset is a real deployment from 6 agriculture patch in Murcia, Spain, one of the Europe's driest regions. Each patch is equipped with sensor measuring soil moisture, temperature, humidity, and weather variable. These variables change dynamically depending on irrigation pattern and environmental condition. In our study, each plot acts as federated client, making the dataset ideal for evaluating federated learning under realistic constraints. Our system follows IoT edge paradigm, where each client performs local model training and send only the model update to the server. The server aggregates the updates and broadcasts the model to all clients. In fact, that raw environmental data never leave the client. Only model updates can do that, which is essential for protecting farm level water usage privacy. The proposed framework integrates security and energy management. We use a lightweight neural network designed for low power devices. Each client reports its available energy, allowing the server to make energy aware scheduling decision. Client with low energy skip some rounds to preserve their longevity, while high energy clients participate in more often rounds. All updates are securely transmitted to the server. Our threat model assumes insecure communication channels without protection. An adversary could intercept the model update or manipulate them to poison the final model. To address this, each client encrypts its update with AES 128 encryption, which is extremely efficient on microcontrollers, and ATAS HAA 256 hash for integrity verification. This choice provides protection while keeping computational overhead below 1%. We implement the entire system using Docker containers, simulate realistic IoT hardware. Each container had CPU and memory to emulate microcontrollers or Raspberry Pis. We run under 13 federated rounds corresponding to 13 months of real agricultural conditions. Energy management is crucial in constrained devices. Each client starts with initial energy budget based on its simulated hardware class. At each round, client compute how much energy they would consume. The remaining energy is too low. They skip training to prevent perimeter shutdown. This mechanism allows the federated learning process to continue even as some devices weaken. As a result, this table summarizes client performance. High energy clients such as client 1 or client 3 complete all rounds, while lower energy clients participate less frequently. Despite this heterogeneity, performance remains consistent across clients, showing the effectiveness of energy-aware juggling. This result is the server results. The global model converges smoothly by round 20. We got a strong predictive performance, and by the 13 rounds we get the best RMSE. This demonstrates that the federated learning system remains robust even with heterogeneous participation. As a key result is that the security layer introduced less than 100% overhead. This confirms that AES 120 and SHA 256 are excellent choice for IoT. They provide meaningful protection at negligible cost. Also, we did a comparison between centralized and federated learning approach. Centralized learning performs slightly better, which is accepted because it has access to all the data. However, our federated learning approach achieves accuracy close to centralized while preserving privacy and accounting for device energy constraint. When we compare our approach with the other methods such as secure aggregation or differential privacy, our approach clearly offers the best trade-off of constrained IoT environment. Stronger mechanisms are possible, but they come at significant energy and computational costs. At the end, this work shows that secure and energy-efficient federated learning is not only feasible but practical for IoT systems. By combining lightweight security and energy-aware participation, we maintain both model performance and device longevity. Our next step is deployment on real IoT nodes and extending the threat model to address poison attack. Thank you for your attention, and I'm happy to take your questions.
Okay, thank you so much. Sorai, are you online?
Yes, I'm here.
Okay, perfect. So, do you have any question? Okay, I have a question. So, your solution in your solution, the training of the model is performed inside the IoT?
Yes, in this case, we are using Docker to mimic the real world conditions.
Okay, but in this case, I think I read that you are using a Raspberry Pi. So for more constrained IoT, I mean, if we are talking about a sensor and so on, I assume that you are not capable of executing a learning inside the IoT, right?
In this case, we are using learning using Docker. So we are not using a real Raspberry Pi, but we mimic the same conditions of Raspberry Pi or any IoT device, and we are using Docker.
Mhm. Yeah, I was talking. I mean, if the IoT is not a Raspberry Pi, because a Raspberry Pi is not so much constrained.
Yeah, yeah, sure.
If you are using more constrained IoT, I assume that you should delegate on a controller or something that aggregates the information from the IoT and trains the model, right? So
Yeah.
in this case, your solution will be applied to the controller, no?
Yes.
Okay, okay. And this is what you were mentioning about the secure aggregation, I think, or it's a different technique.
Because of yes, exactly. Because of that, we are talking about secure aggregation.
Ah, okay, 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 okay. Thank you so much.
Welcome.
If there are no more questions, okay, let's thank Zora.
Okay.
Okay, so I think we have finished the session. So thank you everybody for being here. I hope you enjoyed.
So we are start the last session of the Mobisec this time. So session 8C, this session is about cover threat analysis. So we have 4 presentations, and first 3 presentation will be in online, and the last presentation will be in this session. And so we are starting from the first talk, which is binary lifting into LLVM IR with large language models, and which is written by Seun Jo and Jiwon Lee, Donghoon Lee, Wonseok Choi from Korea University. Okay, so we will start the video here.
Hi, I'm Shinzo from Korea University, and I will present binary lifting into LLVM with large language models. We compile source code to make an executable file. Many modern compilers use an intermediate representation during compilation. Many commercial software, firmware, and programs provide only the binary without source code. But a binary is just an executable file. It is very hard to understand or modify. So, recent work first turns the binary into an easier form and then analyze it. We focus on lifting binary to IR. Decompiling a binary to source code is very active today, but lifting is still not well studied. Source code is good for humans to read, but for automatic analysis, IR is better. Thus, our goal is to get IR directly from binary. We target LFVM-IR. LFVM-IR is the intermediate code used by the LFVM compiler, and many people in research and industry use it today. It also uses static single assignment or SSA. Each variable is assigned it only once. Because of this, it is easier to track data flow, so it is good for program analysis and optimization. LFVM-IR is like a high-level assembly language with time information. Then, why do we choose LFVM-IR? First, LFVM-IR is easier to analyze than binary or assembly. It has a higher level of abstraction and a more regular structure. Second, LFVM-IR is architecture independent. Once we lift to LFVM-IR, we can use the same analysis pipeline for any CPU. Third, it helps with reuse and integration. Code in LFVM-IR can be compiled and linked with DLL, library, and internal modules. First, it is good for security fixes and feature changes. We can patch, obfuscate, or add few features directly at the IR level. Finally, we can use the whole LLVM ecosystem. We can reuse many LLVM tools such as optimization, test generation, and model checking. For lift IR to be useful, it must satisfy some requirements. First, the IR made by the lifting tool must behave the same as the original binary. Second, it must be compilable again and run as an executable. Third, it must be readable so humans can understand and edit it. Finally, the lifting tool should not depend on one specific tool or platform. For example, it should not work only with one version of LFVM or one version of IDA. However, existing lifting tools do not meet all these requirements. Today, the main LFVM IR lifting tools are Regdat and Maxima. The LFMIR generated by Regdat is not guaranteed to recompile. So it is hard to use it in a read to chain or to check the program's behavior exactly. Maxima works well on Linux, but not on Windows. Also, it often breaks if we change the version of LLVM or IDA even a little. In addition, both Regdat and Maxima are rule-based tools. Their lifting rule must be extended and updated again and again. This needs a lot of time and human effort, so maintenance is hard. The IR they generate is also not very readable. This is LFMIR generated by Regdat and Maxima. Inside each function, the basic block names are just memory address offset. Most instructions are only load, store, and branch. The variable names are also just number. So it is very hard for a human to read and understand this IR. So we use an LLM to fix this problem and make the lift IR better. Unlike existing tools, an LLM can understand the meaning of assembly and generate IR. So it is much easier to use even when the OS, CPU architecture, LLVM version, or helper tools are different. Also, our method can make IR that is easier to read than IR from existing tools. As you can see in the figure, the IR from the LLM has meaningful block and variable namespace and clearly show their rules. The control flow is also cleaner and more organized, so the IR is much easier for humans to read. To use an LLM for lifting, we must solve two main challenges. First, the LLM's context window size. A real binary has many instructions, but the LLM can read only the limited number of tokens at one time. So we can't give the whole binary to the LLM in one prompt. Second, the correctness of the generated IR. The LLM may produce IR with syntax error or IR that cannot be compiled and run. Our paper focused on these two problems and how to solve them. To solve two challenges, we split our method into two main phases. First, the data pre-processing phase. Second, an IR generation phase using system prompt optimization. First, I will explain the data pre-processing phase. This phase has two steps. The first step is disassembly. Because LLMs learn from text, they cannot directly understand machine code. So we convert the binary to assembly and use it as input to the LLM. The second step is function filtering. We split the LLM input by function. A binary has many functions, including user-defined system, and external library functions. But we only want the user-defined functions. So first, we use IDA to extract the full function list from the binary. Then we use an LLM to select only the user-defined function. Now I will explain the second part, IR generation. This part also has two steps. The first step is function level IR generation. For each filter function, we use its assembly code as the input to the LLM. The LLM then generates LFMIR for each function. At this step, we design an error-based system prompt. The goal is to make our IR valid, executable, and linkable. First, we use the standard question-based prompt to generate IR. Then we collect the error that occurred during IR integration recompilation. Next, we analyze this error, make rules from them, and design an error-based system prompt. This prompt has 10 rules. Rules 10 to 6 are about LLVM syntax. They cover SSA form, opcode, bytecode, and type matching. Rules 7 to 10 are about making the IR executable. They handle external function, declaration, global symbols, and the target triple. This rule helps the IR compile and link correctly. Now we move to the last step, IR integration. In this step, we use three built-in LLVM tools, LLVMS, LLVM Link, and LLVM Dis. Now, I will explain how we evaluate our method. We use two main metrics. The first metric is the IR synthetic validity rate. This is the percentage of IR file that we can turn into bit code without syntax error. Insert in check if the IR is syntactically valid. The second metric is the re-execution rate. This is the percentage of compiled binary that prints the same output as the original program. So it checks not only does it compile, but also does it behave the same. Now I will briefly explain our experiment setup. We use GPT-5 as the LLM model. Our dataset has 11 algorithms. All of them are written in C. We compile them on Linux with the O0 option. The algorithm include BFS, DFS, binary search, linear search, Dijkstra, and common sorting algorithm, bubble, insertion, selection, quick, heap, and merge sort. Each algorithm has two functions. For the experiment, we use question-based prompt and the error-based prompt. First, I will show the IR synthetic validity result. For 11 algorithms, we generate IR 10 times for each function and then took the average. With the question-based prompt, the average validity is 80.9%. With our error-based prompt, the average goes up to 94.1%. High stability ratio is the percentage of functions whose IR synthetic validity rate is 80% or higher. This ratio increased from 63.6% to 95.45%. So, for most functions, the LLM produces synthetically valid IR in the stable way. Next, I will show the re-execution result. In this experiment, we used the integrated IR for each algorithm. For each of the 11 algorithms, we run type 5 trial and take the average. The re-execution rate is 39.09% with the question-based prompt. With the error-based prompt, it goes up to 79.18%, almost twice as high. We also measure the conditional success rate. This is the re-execution rate only when all function level IR for the algorithm passes the IR validity check. This value also increased a lot from 60.56% to 87.75%. We propose a framework that uses an LLM to lift binary directly into human-readable LLVM IR. We also collect real error logs from the LLVM toolchain and design an error-based system prompt with 10 rules. With this prompt, we reached 94.1% IR synthetic validity and 79.18% re-execution rate. But our work still has limits. We test only small algorithm binary, also use only the O0 optimization level. In the future, we want to test harder cases, program with large code graph, different architecture, various optimization levels, and even obfuscated binary. Our goal is to show that LLM-based lifting also work for large scale and real-world binary. Thank you for listening. Thank you.
Hear me?
Yes, I'm here.
Oh, okay. Thank you. So now we are moved to the Q&A time. So are there any question or comments? Okay. I have a one question. So in your experiment, actually the LMM based one is non-determinism, right? So this is not a deterministic algorithm. So could you give me some future work on according to this sense? Did you get it? Do you have any future work on your? Of course, you already presented it in a last slide, but I mean, so your algorithm is not deterministic. So is there any the future work about this?
The experiment is being conducted as a follow-up studies. We are going to same experiments several times.
Okay. Thank you. So
Can I answer? I'm a co-author of the paper.
okay. Thank you.
In the future work, to justify the experiment result, we are planning to run more justifiable data set. I mean, the more complex binary samples, which can be agreed by the society. So then we have to justify why we have to choose that kind of data set. Okay, that's I think the next work to be done.
Okay. Thank you very much for the comments and your future work, sharing your future work. It is very nice.
Thank you.
So, are there any other question or comments? Okay, there's not. So we will give applause to the presenter. Thank you. Okay. We will move to the next talk. So it is also the online, and the title is Classification of Tor Metadata Combinations for Investigation, and which is written by Isul Che, Jung-At Kim, and Sungmin Kim from Seongshin Women's University. We will see the video.
Hello everyone, my name is Isu Choi from Seongshin Women's University. Today I will be presenting our work titled Classification of Tor Metadata Combination for Investigation. Tor enables anonymity for Internet users, However, it is also widely associated with cybercrime activities, including those occurring on the darknet. As a result, research on de-anonymization has gained increased attention, especially for tracking suspects involved in criminal activities. Prior work primarily focused on de-anonymization, but much of it does not consider the anonymity of reason-limited users, thereby conflicting with Tor community's ethical goals. Moreover, many studies rely on unrealistic assumptions such as global traffic correlation or AS-level adversary, making their approach difficult to apply in real-world investigation. To overcome this limitation, we attempt to utilize internal metadata that Tor already generates rather than externally collected traffic. Unlike prior work that focused on breaking anonymity through traffic level analysis, our goal is to explore addicting feasibility from an investigative perspective. First, we analyzed Tor source code to identify metadata generated during circuit construction. Then, using scenarios targeting hidden service operator and client, we analyzed how internal metadata can function as investigative evidence. We particularly focused on how identifiability changed depending on the visibility scope of the investigator. Tor routes traffic across multiple hops, and each relay decrypts only the corresponding layers, similar to an onion. The guard relays knows the client's IP but cannot see the destination. The middle relay only sees the adjacent guard and exit nodes. The exit relay can observe the destination address but does not know the client. This layered approach forms Tor's core anonymity model. Other components include the onion proxy, onion router, and directory server. The OP is the client-side software responsibility for obtaining consensus documents, selecting paths, and constructing circuit, or refers to relays that forward traffic. DS consists of trust servers that publish the consensus, which provides relay information, bandwidth status, and exit policies. Hidden service provide mutual anonymity through introduction points and rendezvous points. The onion service select random relay as introduction points and registers service descriptor without exposing its IP. When a client accessed an onion address, it selects a relay to serve as its rendezvous point. The rendezvous point enables connection to the hidden service without running the client's IPs. Because both sides remain hidden services are often exploited for illicit activity. Data is transmitted through fixed-site cells consisting of a header and encrypted payload. The header contains the circuit ID and command values like create, relay, while stream-level operations are distinguished using stream IDs inside the payload header. Thus, circuit ID, command type, and stream ID act as valuable metadata for communication tracking and circuit management. SAR conceals traffic patterns and prevent observers from inferring packet size. Each relay decrypts only one encryption layer, meaning no individual relay can view full content. Only at the final exit does the actual TCP payload appear. Therefore, onion-style encryption combined with fixed-size cells provides strong anonymity guarantees. Tor communication follows a hierarchy structure of 1 to N to M, representing channel, circuit, stream. Multiple circuits are multiplexed over a single TLS channel, and multiple streams are delivered within one circuit. Consequently, metadata such as channel ID, circuit ID, and stream ID is necessary to manage each independent layer. Based on this internal architecture, we analyzed the life cycle of a circuit and identified metadata generated at each stage. Tor pre-builds circuits for multiple purposes and manage them in a pool. When users' requests arrive, Tor selects an appropriate circuit or generates a new one. After usage, circuits are detached from related objects and removed from the circuit list. Before creating a circuit, Tor selects a sequence of relay that meet requirements such as purpose or connection configuration. The selected OR information is stored in origin circuit T CPath, and OP-generated circuits are tracked in the origin circuit side. At each step, Tor generates command cell with corresponding pairs and exchange them hop by hop. When circuit extension is complete, the circuit is registered into global circuit list and streams are bound for data exchange. A circuit is terminated when stream transmission completes, when either timer expired, or when decryption failures occur. The termination reason is recorded in marked for close reason, and pending circuits are moved into circuit pending close. Then, Tor removes the circuit from global list, send destroy cell, and free memory. Next, we introduce investigation scenarios that assess whether metadata visibility can aid in identifying hidden service operator and their clients. Tor intentionally surrogates what clients and relays can observe, enhancing anonymity but also restricting auditability. Operator serves as infrastructure provider rather than mere users, thus identifying them is crucial for dismantling persistent, illicit service. Meanwhile, clients may resell or misuse access, increasing criminal exposure. Our goal is to disprotimate these roles based on metadata obtained from these nodes. We analyze which metadata and identifiable attributes become observable depending on the acquired node. In vanilla Tor, metadata remains only in volatile memory. Therefore, we assume that relevant metadata is explicitly loaded so that investigator can retrieve it when the node is exceeds. A host PC belongs to the OP side, making it the most informative vantage point. Internal circuit and stream states, cell level information, and circuit purpose are directly observable. Additionally, edge connection T, hidden service ident, allows distinguish whether the pitch was handling hidden service traffic, either as operator or client. Channel timestamp can further reconstruct communication timeline. Circuit purpose help discriminate operators from clients. An operator constructs circuit support choose introduction points, whereas a client chooses rendezvous points and delivers rendezvous points information to the operator. Thus, identifying circuit purpose allow inference about hidden service-related activities. If the investigator obtains entry or middle relays, they can assess whether previously identified hidden service circuit were actually used. Matching channel circuit ID pairs along with increased cell counters imply real communication activities. Furthermore, canonical OR port in relay connection object reveals the actual IP port of connected nodes. When host PC entry and middle relays are available, exit logs mainly serves as a cross-validation source. Matching timestamp between OP side logs and exit relay traffic logs increase confidence that the circuit persists until exit transmission. Summary of metadata importance. The most discriminative metadata lies on the OP side, especially circuit purpose, which helps determine whether the user is a hidden service operator or a client. In summary, we classified Tor metadata based on visibility scope. Depending on where information becomes identifiable, the anonymity guarantee of unrelated users are compromised, which directly conflicts with Tor community's principle. As future work, we plan to explore XGX Tor to balance investigative needs and anonymity by storing only minimal metadata securely and making it selectively available. Thank you for your attention.
Thank you for your nice presentation. So, can you hear me?
Yes, I'm here.
Oh, okay. So we will move to the Q&A. Are there any question or comments? So I have a one question. So the last of your slide, so there was a future work, and actually I'm not I'm not a specialist in this area, but it is very impressive because as I know, it is like a first result, like a primary result on this area, like a Tor metadata you're using, and also you investigated it in this metadata. But you also mentioned about that there is some trade-off, the anonymity, and also the is investigation. So you mentioned that you are using the SGX Tor. But I barely know about it. But could you explain it a little bit? SGX Tor.
SGX Tor is trusted. SGX is trusted execution environment. So as we plan to explore methods for securely recording and utilizing metadata by developing a module that runs in SGX. So we aim to balance performance, consideration, and maintain Tor's core anonymity guarantees while adding a layer of auditability. Yeah.
Oh, I see. So, so in that sense, how could you uh, preserve the anonymity during your investigation? Could you briefly explain it?
The anonymity is not if relate the SGX.
Ah, really? Okay.
Yeah.
Oh,
Can I
uh,
pick up the answer?
yeah, yes, yes.
One of the author here.
Thank you.
And
Yeah.
basically, SGX, one of the representative trusted execution environment guarantees that code and data reside in the trusted region, preserves confidentiality and integrity of the executed code. So by leveraging such technique, we can preserve the confidentiality of metadata when it is executed, because it is executed within the isolated execution, which preserves the confidentiality. But what we want to do is further explicitly separate out some Tor metadata, which can be used as a side channel for revealing some breaking the anonymity or kind of attack.
Yeah.
So we try to make explicit trust model that some of the Tor components are separated and run within the T, and it does not actually stores other than metadata that which can be further used for investigation. So that's what we try to further proceed.
Oh, okay. Thank you. It makes sense, I think. So I think it is a promising direction. Thank you for the comment. So are there any other question or comments? If not, so we give a big applause to the presenter. Thank you. Okay, we will move to the third talk, and upswing transformer-based multi-class obfuscation classification for Windows Portable executable, and which is written by Jun-hyuk Kang, Jae Lee, Won-seok Choi, and Dong-hun Lee from Korea University. So we will see a video.
Hello everyone, my name is Junhyuk Kang from Korea University, and today I'm going to present our work titled OBF Swin Transformer-based multi-class obfuscation classification for Windows Portable executable. Here is the outline of my talk. Let me begin with the motivation. In recent years, a large portion of new malware still targets Windows PE malware as the main format. At the same time, the use of commercial obfuscation tools has become very common to evade analysis. Obfuscation transforms the structure and semantics of a binary to hinder analysis. Attackers can easily apply these techniques using commercial protectors, while security solutions struggle because this obfuscation layer hides the malicious behavior. In this context, being able to accurately identify which combination of obfuscation options are applied to a given binary is a very important first step. It can guide subsequent deobfuscation, sandbox configuration, and signature or model design. Prior work suggests that obfuscation and protection techniques remain among the most challenging aspects of malware analysis. Importantly, modern malware often use multiple obfuscation options simultaneously and in a nested way. For example, virtualization and string encryption and anti-debugging can all be combined in a single sample. In such cases, the effect of obfuscation is not simply additive. The interaction between options leads to nonlinear changes in features. So therefore, we argue that this is more practical to treat the entire combination of options as a single class. Our goal is this work is to perform multi-class obfuscation, classification over these options combinations, not just the individual options. This slide summarizes the related work and how it differs from ours. First, Parker et al. Focus on source code obfuscation, so the target is simpler than our setting of commercial obfuscated Windows P binaries, and they do not classify option combinations. Second, Pham et al. This studies IoT Linux malware using electromagnetic signals from the device. This is a dynamic and device-dependent setup, and it does not deal with binary obfuscation or option-level classification. Third, Dania et al. Also targets source code obfuscation in the Android environment. Again, this is different from Windows P binary obfuscation with commercial tools, and it does not classify detailed obfuscation options combinations. Fourth, Lee et al. Pack genome. This study automatically generated Yara rules to recognize different packers. It is effective at identifying packer families, but it does not perform fine-grained classification of which obfuscation or packing options are combined in the individual P binary. So existing work does not directly address our problem of commercial Windows P binary obfuscation and static multi-class classification of single obfuscation options combinations. In this work, we specifically target binary obfuscation on Windows P and propose OVF Swin, which uses 3D Markov images to statically classify various commercial obfuscation option combinations. To understand our method, I'll first briefly explain the Markov image. As shown in the slide, a Markov image is visualization of the transition probabilities between bytes in a binary file. It represents how likely one byte state is to move to the next. Essentially, we map the binary code into a matrix and then convert it into a visual form. This allows us to see characteristic patterns of the binary. While the standard concept shown here is based on 2D transitions, it is important to note that in our actual framework, we extended this into 3D. By doing so, we significantly increased the information density and capturing much richer patterns than the traditional 2D approach. Next, let me briefly introduce Swin Transformer. Swin Transformer is a vision transformer architecture that uses Windows-based self-attention and a shifted window mechanism to efficiently capture both local and global patterns in images. It has a hierarchical structure where patch merging reduces spatial resolution while increasing channel dimension, enabling multi-scale feature extraction. This design keeps the computational complexity nearly linear in the image size, which is important when dealing with relatively high-resolution images. In our setting, obfuscation affects both local byte-level patterns and broader structural layout in the binary. Therefore, a model like Swin Transformer, which can combine local and global context efficiently, is a good fit for classifying patterns in Markov images. Now, I will introduce our proposed framework, OBF Swin. As shown in the figure, the pipeline consists of 3 main steps. Step 1 is preprocessing. We convert the raw input binary into a 3D Markov RGB image to visually capture its internal patterns. Step 2 is classification. This image is fed into the Swin Transformer model. The model extracts features to effectively identify complex, overwrapped obfuscation techniques. Step 3 is the result. Finally, OBF Swim predicts the exact combination of obfuscation options applied to the sample. Since this entire process is purely static, it remains safe and scalable for large-scale analysis. The first detailed step in preprocessing is constructing the 3D Markov matrix. We read the P binary as a raw byte sequence, and then for every consecutive triple ijk of bytes, we count how often the transition I to j to k occurs. After normalization, we obtain a probability distribution over all 3D possible transitions. The key design choice here is to keep the three-step transitions instead of collapsing them into simple pairwise transitions. This helps preserve richer information about patterns that arise from obfuscation. As a result, we can better capture the distinct transition patterns induced by different obfuscation options and their combinations. However, a full 3D matrix is extremely high dimensional and expensive to handle directly. To address this, we reshape the 3D Markov matrix into a suitable form, apply principal component analysis, and extract the top three principal components. We then map these three components to the R, G, and B channels of an image, producing a 3D channel Markov image. This approach preserves most of the variance in the original transition distribution, converts the representation into a standard RGB image format suitable for vision models, and significantly reduces the computational and memory footprint. In short, complex obfuscation patterns appear as visual textures and structures in the Markov image, and the swim transformer learns to recognize these patterns. This slide shows example Markov images generated by preprocessing pipeline. Each image corresponds to a binary with a different obfuscation option combination. Finally, let me explain the model implementation and label design strategy. We choose swim transformer for three main reasons. Window-based self-attention captures local byte patterns effectively, and the shifted windows and hierarchical architecture integrate global structural information. The nearly linear computational complexity with respect to image size makes it feasible to process Markov images efficiently. An important design point is label space separation. Instead of training a single model to predict all possible combinations at once, we train our models specifically for 2-option combinations and 3-option combinations. This separation allows each model to learn decision boundaries tailored to a specific combination size. Experimentally, we observed that this strategy reduces inter-class confusion and improves overall accuracy compared to a single large model handling all combinations. Let me now describe the evaluation setup. We use the public BODMAS dataset, which contains Windows P Moreau samples. On top of that, we build a real-world dataset of Windows P Moreau and apply various obfuscation options using a commercial protection tool, VMProtect. Overall, we construct around 100K samples covering 2-option combinations and 3-option combinations. Each sample is labeled with its corresponding obfuscation configuration, and we use this dataset to evaluate classification, performance, and the impact of label space design. Here are the main results. Our framework archives outstanding performance on the test sets. 94% accuracy for 2-option combinations and 96% accuracy for 3-option combinations. However, if we look closely at the confusion matrix, we can observe some interesting behavior caused by the packed output file or PA option. First, in the 2-option subset on the left, the PA option tends to dominate the byte patterns because it compresses or encrypts the entire binary body. Consequently, weaker signals from options like import protection or IP get masked. This is why you see a slight accuracy drop in the IPPA class. It becomes harder to distinguish from other PA-based combinations. Similarly, in the three-option subset on the right, we see that PA flattens the signatures of both memory protection or MP and import protection or IP. This makes the MP-IP-PA combinations nearly indistinguishable from other triples that contain PA. Despite the strong masking effect of the packer, our model successfully captures the subtle nuance in the vast majority of cases, maintaining high overall accuracy. To conclude, let me summarize the contributions and discuss future work. In this study, we proposed a static framework for identifying multi-option obfuscation applied to Windows PE binaries. Introduced the 3D Markov image representation derived from byte-level transitions, combined with a swing transformer for classification. Demonstrated on a dataset of our BODMAS samples that we can archive 94% accuracy for two-option combinations and 96% accuracy for three-option combinations. Our approach operates purely statically without executing or disassembling binaries and does not rely on high-level metadata, and making it suitable for large-scale and safe analysis of malware collections. As for future work, we observed that the unified model for all combinations reaches only around 67% accuracy. To address this, we plan to explore curriculum learning, where we gradually increase the complexity of labels and hierarchical prediction architectures, where the model first predicts high-level categories and then refines them. Our long-term goal is to build a more comprehensive model that can handle a much larger and more realistic space of obfuscation options and combinations, while maintaining robust performance. This concludes my presentation. Thank you for your attention. I'd be happy to take any questions.
Thank you. Thank you for your nice talk. And can you hear me now?
Yes, I can hear you well.
Okay, thank you. So we will move to the Q&A. So are there any question or comment? Okay. Okay, from me, I have one question, but it is not a question. I just I barely know about this area. I'm sorry about that, but I'm really happy that I'm familiar with some Markov transition matrix. So you mentioned. So in that sense, so actually there is a theory about the expander graph, and which is the very useful metrics that we can do it in a network theory, and so it increases the randomness if it is moved to the transition phase. So I know several types of this kind of a very optimal expander graph, like a Markov chain graphs. So is it possible to apply the new Markov chain, Markov transition matrix, which has a very nice randomness? Is it make sense? Does it make sense?
Sorry, but can I ask you a question again?
Oh, yeah. So you used a Markov transition matrix, right?
Yeah, that's
Yeah,
right.
yeah. So if we have another good Markov transition matrix, which is in some explicit construction in some number theory or graph theory, so is it applicable to your work? or improve your work?
어, 음,
Maybe from the your bit data is transformed to the Markov matrix, right?
yes,
Yes,
right.
yeah. In that sense, if we have another good assigned Markov matrix, if we make so, which is guaranteed the good randomness, then is it good for your research or? Maybe I'm sorry. It is just my special area, so I'm very interested in your work, especially about the transition matrix. Uh, so I hope that there is a chance to we can talk about this kind of some new Markov matrix. So this is just a comment. Okay.
Am I right to ask
Mm-mm.
if the new Markov image is suitable for my work?
Right. That's the point.
The the new Markov images mean 3D Markov matrix, right?
Right. Yes. I think it's possible to make. Yeah.
I think our 3D Markov representation aggregates 3-gram transitions as shown on the slide I to J to K. So it encodes higher order contextual transition patterns and therefore retains richer information than baseline 2D.
So yeah.
Yeah.
So because when we construct the that kind of Markov matrix, so we can also use the quaternion algebra, and quaternion algebra has four bases, like a 1, I, and j, and I j. So it is actually very adaptable to your 3D matrix, I think. And from this quaternion algebra, we can make some kind of a matrix, which has a Ramanujan graph, which is an optimal expander graph. So maybe I think it is possible to adapt to your work. So what do you think? Does it make sense?
I think that's also good for my research to consider in the future.
Yeah. Thank you. So I will contact you. Yeah. Thank you.
Thank you, sir.
Yeah. So are there any question or comment? No. Okay. Thanks to the speaker, the third speakers. Give him applause. So this is not end of this session. So we have another last talk from the session 3B, Advanced Cryptography. And the title is Deniable Kyber, a post-quantum deniable chem scheme, and which is written by Xingming Sun and Po Wen-chi from National Taiwan Normal University in Taiwan.
Hello everyone, I'm Sun Shiming from National Taiwan Normal University, and I'm today to talk about denial kyber, a post-quantum deniable chem scheme. So I will start from introduction, and I'll give some definition and introduce our deniable chem scheme, and show the performance and give a discussion, and then conclusion. So let's start with introduction. So as a start, I want to start with a question that is why we need deniable encryption. So when using regular encryption, we can encrypt a message and then decrypt the ciphertext to get the original message. But when the ciphertext is cut by the cursor, and this cursor acts us to decrypt the ciphertext, then we can only give our secret key, and a secret must be revealed. But when we using a deniable encryption, we still can decrypt the ciphertext with the real key to get the original message. And in this situation, when we being coerced, this time we can give a fake key to reveal a fake message, and we can even provide a fake proof to trick coercer. So now we know why we need deniable encryption, but why we need a post-quantum deniable encryption. That is because most of current deniable encryption are based on the integer factorization and discrete logarithm problems. And those problems are considered easy to solve by a quantum computer, so they are considered not safe in the near future. So to face this situation, NIST started a process to recruit some standardized quantum resist public key cryptographic algorithms in 2016. And Kyber is the only CAM that is accepted in the competition. So in this work, we construct a deniable encryption scheme by modifying Kyber CAM. So I'll give some definitions. So in our definitions, there are our deniable CAM scheme are consist of following algorithms. And as we can see, there are two sets of algorithms. One is for normal and one is for deniable. And we prepare a verifiable algorithm to trick the coercer. I introduce CyberCam. CyberCam is a CAM which the security is based on modular learning with error problem. It first used NLWE-based encryption to construct a CPS secure PKE scheme, then used Fujisaki Okamoto transform to construct a CCA secure CAM scheme. And Kyber's CAM consists of three algorithms: key generation, encapsulation, and decapsulation. In key generation, Kyber can set out a NLWE problem. And in encapsulation, it first generates a message and then hash the message into a pseudo key and random seed. Then use this random seed to encrypt the message to a ciphertext. And then hash again to get a key. And in decapsulation, it first do a re-encryption. That is, it first decrypt the message and then hash to the pseudo key and random seed, then encrypt again to get a ciphertext. And the algorithm then check the results to the original ciphertext. If they are the same, then output a same key. And if not the same, then it output a random key. So let me introduce our deniable CAM scheme. So I will show this by describe how we modify the original scheme to our deniable scheme. So we now want to achieve a deniable encryption, so we need two keys. But one set of CAM only produce one key. So we need two sets of CAM to produce two keys. But how to merge these two CAMs? So when we look into the original scheme, we'll see two problems. The first one is in encapsulation. we now have two ciphertexts, but we only want to output one ciphertext. And in decapsulation, after the re-encryption, it compared to the ciphertext, but we now have two ciphertexts to compare, so we need to compare those in the same time. So for the first problem, we use Chinese remainder theorem to merge the ciphertext. In key generation, we produce some parameters, and in encapsulation, we use those parameters to merge the ciphertext. So when we're doing this, when we module with Q0, we can see the coefficient with Q0 will eliminate. And by our assumption, P1Q1 is equivalent to 1 mod Q0. So we can recover the ciphertext under module Q0. For the second problem, we use chameleon hash. The one value can be used in two camps. Chameleon hash is like a normal hash with trapdoor. With trapdoor, given two messages, N0, N1, and a random R0, we can efficiently compute R1 such that these two hash values are the same. And without trapdoor, it's hard to compute R1 and it's more like a normal hash. So with chameleon hash, we can modify the verification step as follows. So in encapsulation, we generate a hash function and find a collision and let these two hash values be the same. In decapsulation, we rebuild the hash function and check if after the re-encryption, if the hash value is equal to the original hash value, then we output a key. If not, then we output a random key. So next problem is how to let coercer check if a key is valid. So here we add a coin in a verify algorithm. So after encapsulation and decapsulation output a key, we generate a coin corresponding to the key. And when the coercer wants to check a key is valid, it runs a decapsulation to get a key and coin, and compare to those the sender provide. If they are the same, then the key is valid. So the next problem is how to convince the coercer that there is only one key. So here we use multi-distribution model, means that as we can see before, we have a set of normal algorithms and a set of deniable algorithms. And we claim we are using the normal one. For normal algorithms, we replace everything about the second key with random. So let me do a summary. In our deniable algorithms, there are two sets of camps. And to merge these two camps, we use Chinese remainder theorem and chameleon hash. And in order to let coercer check a key is valid, we add a coin in a verify algorithm. And to convince the coercer there is only one key, we use multi-distribution model. We prepare a normal algorithms which replace all parameters about second key with random. So here is our performance and discussion. We simulate the experiment by using existing CyberCAN's code and chameleon hash code. We run the experiments with this prime twice to simulate the running time of two camps and implement our scheme with chameleon hash. So since our scheme need two sets of camp, we can see the running time of deniable key generation and decapsulation is about 2 times of the original key generation and decapsulation. And we can see there is a big gap between our encapsulation and the original encapsulation. And this is caused by the key generation algorithm of convenient hash. We claim this can be improved by using more efficient convenient hash algorithm or generate keys for convenient hash by sender in advance. Here I want to give a discussion is that since we are using the Chinese remainder theorem to merge ciphertext, so one may ask how we can say our scheme is secure despite we generate two cans under different prime modulo. So in fact, our deniable can scheme is still safe even if we reveal all the primes we use. This because the security of this scheme is based on the secret key. One will not decapsulate key correctly if they don't have the corresponding secret key. So we can assure that our CAN scheme is safe even if the integer factorization problem is being solved. So let me do a conclusion. In this work, we construct a bi-deniable multi-distribution key encapsulation scheme. For performance, the running time of deniable key generation and decapsulation is about 2 times of the original scheme, while encapsulation and deniable encapsulation has a significant growth compared to the original encapsulation. And this can be improved by using more efficient algorithm or generate keys for convenient hash in advance. And despite we use Chinese remainder theorem to merge ciphertext, the security of our scheme is based on the secret key, so our CAN scheme is safe even if the integer factorization problem being solved. So there's my presentation. Thank you for listening.
Okay, thank you for your nice talk. So, are there any question or comment in online? Okay, okay. So yeah, thank you for your nice talk. So I also I'm very interested in your work. So you use the Chinese remainder theorem in your construction, and so you said that it is safe in even integer factorization is solved, but really so when you added it in the Chinese remainder theorem, could you get back to the Chinese remainder theorem? Yeah.
Here.
Yes, here. Okay. So it seems like it is solvable by the integer factorization problem, but could you explain it more specifically why it is safe even in
Yes. Right.
So the Chinese remainder theorem is applied in this here?
Here is the original Kyber CAN scheme, and the first step of the decapsulation is to decrypt the ciphertext with secret key. So we claim that if one not get the secret key, then it will not decrypt the message correctly. So it will be secure.
Yeah. I see. Okay, and another question is the chameleon hash function part. So as I know, maybe the chameleon hash function has some homomorphism property. So what kind of
in my knowledge, I think it's no. Maybe one can do it.
I see. So there is some result. So if we have a homomorphic one-way hash function, then we can make the chameleon hash function or something. So maybe it is expandable, and also maybe we can. So specifically, so what kind of a chameleon hash function you used in your construction? No, it is just some abstract one, or do you have any instantiation of this chameleon hash function? Specific chameleon, or just a theoretical approach?
So I don't remember the real name of that scheme. So
I see. So you have anyway you have a actual some chameleon hash function.
Here, it will be just a plan that if I have a chameleon hash function, then I can do this, and we just use existing chameleon hash code to simulate it. So yeah, it's just a simulation.
Okay. And another last question is: are there any similar approach on a digital signature or digital signature, like a deniable signature? I'm not sure that it is makes sense or not. But if you have so you did it at the Kyber, and there is a dilithium, right? Dilithium, crystals dilithium, which is the standardization of the NIST in signature. So if you applied it like a Chinese remainder theorem and also the chameleon hash, could you do it a very similar concept on deniable signature or something? Does it make sense?
So I have no knowledge about the other schemes. So yeah.
Okay. Maybe we can talk later. Yeah. Thank you. So yeah, are there any other questions or comment? Okay. Okay, we finished all talks in this session, and I will conclude my session. And this is the last day of the Mobisec, and this is the we will close. And I really appreciated your participation and also your valuable contributions for this Mobisec. Sincerely, I thank. So okay. Give a big applause to this closing this session. Thank you.